Hi everyone, I'm Sudipta Das. I'm from Vishwabharati Shantiniketan. I will today talking about study of pressure parametric dark energy model in the framework of F of Q gravity. So the plan of the talk is as follows. First, I will give a brief introduction about the F of Q gravity theory. Then I will formulate the basic uh, basic structure of F of Q gravity. In this context, I will describe a pressure parameterized model, and finally I will discuss the results. So we know that in general relativity, the geometric aspect of this gravitational interaction is performed in terms of its space-time curvature, and this is a standard interpretation of gravity that we know. But there are few alternative interpretations as well which one can have. So in flat spacetimes, apart from this curvature, the gravity can be fully ascribed in terms of either torsion or non-metricity. I'll come to this. What does this mean? So if the spacetime geometry or gravity is described in terms of torsion, then that geometry or that theory we call it teleparallel equivalent of gravity. And if it is described in terms of non-metricity, then we call it a symmetric teleparallel equivalent of gravity. So basically what we have is we have three seemingly unrelated representations of the same underlying theory, which actually all of them give us the same description of gravity. All of them give us the description of gravity, but it seems that they are completely unrelated. So before we proceed, let us try to understand what we mean by curvature, what do we mean by torsion, and what is non-metricity. So let us try to understand this in terms of this diagram, which I have taken from this paper of Jimenez et al., who have basically introduced this non-metricity term. So suppose we have a vector, and if a vector is transported along this closed curve, then obviously this rotation of this vector, it gives rise to what is known as the curvature. And this is the basic theory of general relativity. Whatever field equations or whatever equations we get in general relativity, this is basically based on this curvature of this space. On the other hand, suppose we do not consider the rotation of a transport of a vector along a closed curve. Rather, suppose we have got two vectors and we parallelly transport these vectors which were earlier forming a parallelogram. And suppose we transpose these vectors and we find that they're transported, but the parallelograms no longer form a closed curve. Rather, this non-closure of these parallelograms when these two vectors are transported along each other, then this non-closure basically it gives rise to torsion, and this theory is known as the teleparallel equivalent of. On the other hand, suppose we have a vector and which is transported along a closed curve, and obviously the length of the vector will be changed. So the variation of the length of the vector as it is transported is given by the non-metricity. So the difference in the length of the tensor will give rise to non-metricity, and this theory is called the symmetric teleparallel equivalent of gravity. This non-metricity means that one cannot write down this geometry in terms of a metric form, and that's why we tell this non-metricity. So what we know that the curvature, it measures the rotation experienced by a vector when it is parallelly transported along a closed path. Non-metricity, it will measure how much length of vectors change as we parallelly transport them, so that the metric spaces the length of the vectors is in metric space, the length of the vector is constant. Whereas torsion, it gives a measure of the non-closure of the parallelogram formed when two infinitesimal vectors are parallelly transported along each other. We can understand this in terms of these various connections as well. Suppose this pink color set or this pink color circle, it represents vanishing non-metricity. That means in this region the non-metricity, there is no, one can write it in terms of the metric components. The blue color, it represents that in this portion there will be no torsion, and this green color, this light green color, suppose it represents that the curvature will be vanishing for this. Now suppose if we consider only the geometry where the non-metricity is vanishing, but the curvature and torsion may remain, then we express these connections in terms of Riemann-Cartan connections. If we have this in this region, it will be only described in terms of a torsion-free geometry. In this region, where in this light green portion region, obviously everything it's basically the teleparallel gravity, where the connections will be described in terms of the curvature, in terms of non-zero curvature, but the torsion and the non-metricity will remain. But suppose if I come here in this region where we don't have it's vanishing non-metricity, that means the metric can be written for this geometry. One can write down the metric, and also there is no torsion. In that case, so it's vanishing non-metricity and torsion free. So only the curvature remains, and that is what is our Riemann curvature, which we do in general relativity. If all these three vanishes, then we get our normal Minkowski space. So these are the various subclasses of this metric affine geometry, and depending upon which parameter we keep 0 and which parameter we keep non-zero, we will consider these different connections. So in symmetric teleparallel equivalent of general relativistic theory, a spacetime is characterized by a curvature-free and torsion-free linear connection in conjunction with a metric tensor. For example, in symmetric teleparallel gravity, this will be basically curvature free and this will also be torsion free. So only the non-metricity term will affect. So it is a geometrical theory of gravitation which is constructed in a flat and torsion free geometry. So affine connections obviously will be compatible with non-zero curvature and with zero curvature and torsion, such that the Lagrangian is basically written in terms of the non-metricity scalar Q. I'll define what Q is. And this formulation of GR is arguably considered to be the simplest among the three equivalent representations because there is no curvature, no torsion, and no non-metricity. And only non-metricity is left as the fundamental geometrical object. So let us try to look into the structure of the gravity theories based on non-metricity. The covariant divergence of the metric tensor in this formulation is given in terms of Q, which is known as the non-metricity tensor, and it is derived as the covariant derivative of the metric tensor. From this one can determine the deformation term. Deformation term will basically give a measure of the change in this length, and this is given in terms of Q in this form. We also define a term known as the non-metricity scalar, which is defined in terms of Q and P, where P is basically derivative of this non-metricity scalar. So this P we also call it as a non-metricity conjugate. Using this non-metricity scalar Q, one can write the action for the FQ gravity in terms of this. Where FQ is basically any general function, any functional form of this non-metricity scalar Q. And if you vary this action with respect to the metric tensor, one can obtain the corresponding field equations which are written in this form. This is not a very straightforward calculation, but one can do it. Now, if you consider especially a flat, homogeneous, and isotropic FW universe, then the field equations are given in this form, where because of the modification of this gravity, modification of the affine connection, this left-hand side of this Einstein equations will be modified. Now, for an FW metric, the non-metricity scalar, which is given, it's very simple, and it turns out to be 6h square. So here FQ, it represents dFdq, and FWQ, it represents the second order derivative of this function with respect to Q. Now this field equations one can obviously recast by taking this f of Q on this side. One can recast in this form such that it looks like our usual Einstein equation. So this is the basically the part which will get usually in GR for a FW metric 3h square and so on. We have obviously put 8 by g is equal to 1, and accordingly we will get a conservation equation for this. We haven't specified what rho is. So the idea is that if we choose a functional form for f of q, and if one can find out rho, then from this, whatever contributions we are getting for this f, the idea is whether we can obtain this to, we can use this to obtain the characteristic of dark energy. So we choose an unjust for fq as this. Fq is beta q to the power n. So our rho, it takes this form, simple form, 6fq square minus f by 2. The pressure term, it can be written in this form, and obviously the second Einstein equation, h dot equation, and it comes out. Now the usual practice is, if you want to solve these equations, the usual practice is either one can consider a parametrization for h. We have already chosen f, so fq is known. So one can choose a functional form for h, and one can find out what rho is. But instead here what we do is we choose a parameters form for the pressure, total pressure. So we choose a polynomial form for the pressure component p as a function of z. Now obviously one can ask why this particular form. What is the purpose of choosing this pressure? Now since this parametrization is basically a useful tool where one can choose a particular form of any cosmological parameter and find out the rest of the parameters in terms of this. So we choose a pressure form of pressure parameter, as not many forms for pressure parameterization is available in literature. Also this form of pressure parametric form, it avoids the big rip problem, because at z is equal to 0 one can say this will give you pa plus pb, and then also at z is equal to infinity also this will not blow up, rather we will get it, or sorry, rather at z is equal to minus 1 also this will not blow up, and we will get a value of pa plus pb. So it avoids the big rip problem. Now, using this pressure parameterized form, one can find out the expression for rho z as well as the expression for the equation of state parameter W. Now, one can see when we obtain the expression for rho z, we have a term like some constant k1 into 1 plus z cube. So, one can consider this as the contribution from the network sectors, and the rest of the part which is there in rho z, that can be considered as a contribution from the dark energy part. And one can check whether this gives us sufficient acceleration or sufficient negative pressure to drive the present acceleration. So this quantity, if we consider as the rho dark energy, and this quantity if we consider as the p dark energy, because for normal matter component we know p m is equal to 0, one can write down the equation of state parameter for W dark energy, where eta and omega 0 are two parameters which has been described in terms of rho 0, pa and p. Now with this one can carry out the numerical investigation, and we have to obtain the observational constraints for this on these different parameters for various data sets, and we have found that the interesting values are for this p and p. We can find that these values of p and pb, they come out to be sufficiently negative, large negative values, which indicates that they have the potential to drive the present observed acceleration. So we have also performed the Monte Carlo analysis for this parameterized form, and the prior values chosen are shown here, and one can show that this H0 value, it comes out to be around 71 for Hubble dataset. For supernova, once we input the supernova dataset, the value comes out to be less, but otherwise it comes out to be 71. So this model, it has a potential to not to solve, rather to elevate the Hubble tension also to some extent. We have also performed the model comparison through this AIC and BIC analysis. The AIC and BIC, the definitions of AIC and BIC components are given here. We know that AIC and BIC one can calculate from the maximum likelihood function, where k is the number of parameters and n is the number of parameters and k is the number of observables. So this tells us that this AIC and BIC, if it's positive, if it's less than 6 or less than 7, then we can say that these models are in good agreement with the observational data. And here we can see that for most of the cases, the values of delta AIC or delta BIC are less, which indicates that this FQ gravity model is in good agreement with the observational data. We have also plotted the equation of state parameter for this for this uh, equation of state parameter for this observable values which you have obtained for the by performing this operation. And we've also plotted the age, which shows that with at the present means with evolution the value of age is decreasing. We have also performed the cosmographic analysis for the model, where this is basically the RS parameter. So if S is greater than 0, that is, if S is greater than 0, it indicates a quintessence-like model, while if S is less than 0, it indicates a phantom-like model. And one can see that for all these data sets, we have plotted for it for treatise, all these data sets initially, it goes along Z. So initially the model, it exhibits a quintessence behavior, but in future this effective gravity model will evolve. We have also plotted the growth rate weighted function f sigma at z, and it also shows that the FQ gravity model, it is not very compatible with the observational data. These blue curves, they indicate the observational data, but obviously one can at low shift region this is compatible with the observational data. So in this work we have tried to attempt to describe a dark energy model in FQ gravity model by considering suitable parameterization, and the ICA and BIC values indicate that the pressure parametric model, it shows it's comparable, it indicates a compatibility with the observation. Thank you.